Hi, you guys. This is Mrs. Bolin here with your notes for your Unit 9 review number 2, which means you have a test tomorrow on this. So I'm going to go ahead and go over it and try to answer as many of your questions as I can, even though I can't hear your questions. I'm going to try to explain all these. So for this first one, remember that when we are multiplying with the same base, we can add up the exponents. So if I have negative 2 nines and I've got positive 4 nines, then all together I have positive 2 nines. But remember, and really what this is it means that we're multiplying by 4 nines and I'm dividing by 2 of them. That's what that negative exponent means. But it also works when we just add the exponents. That's the rule for it. But the reason why is because we're multiplying by this many and dividing by that many. Remember that when you have a number that we can simplify, I shouldn't leave it as 9 squared. I should say, oh, well, I know that's 9 times 9, which is 81. Okay, question number 2, whenever we have an exponent, a power raised to a power, we multiply those exponents. So I have j to the negative 16, which means I'm dividing by 16 j's instead of multiplying. So the way that I would write that would be 1 over j to the positive 16. You can also think about it as we're doing the reciprocal of it. You can also think of it as being negative means that it's unhappy where it is. So in order to get it happy, I move it to the bottom. And now it's happy as a clam, whatever that means. Like our clam's really happy. Who knows? Okay, so looking at number 3, remember that when we are dividing, we subtract the exponents. But what I want you guys to think about, because we have to leave our answer using positive exponents, is I always ask my students, where do we have more x's and by how many? So because there are 7 up on the top and 9 in the bottom, we have 2 extra x's in the bottom because 7 of them will cancel off. Anything that's the same in the top will cancel with something the same in the bottom. So I've canceled off 7 of them. I still have 2 extra x's left over in the bottom. So the way that I write that is 1 over x squared. Looking at problem number 4, oops, I forgot to put a box around that one. Looking at problem number 4, remember what I told you guys in other videos. Maybe if this is your first one, you haven't heard me say this, but this negative right here just means that we're taking the reciprocal. So I can go ahead and flip that over before I even start this problem, and it's going to make it way easier. So what I can do is I can say, well, that negative will flip this fraction. So I would have 4y to the third, and I don't really have to write over 1 because divide by 1 doesn't change my answer. 1 divided by something is significant, but if I'm dividing by 1, that doesn't change the value that I have, okay? And then this now, instead of being a negative 2, is a positive 2. Now remember that this exponent gets multiplied by every exponent that's in there. Even though you can't see the exponent on 4, it has like a little imaginary 1 that we don't write. We've got 1, 4, so we don't really need to write the 1, but it's there. So if I go 1 times 2, I have 4 to the 2, and then I do 3 times 2, and I get 6. Remember what I told you up here for number 1, anytime you have a number with an exponent, we can simplify that, especially when it's these lower numbers. 4 squared is 16. So that one's super easy to simplify. If it was like 7 raised to the 8th power, I would be tempted to leave it like that. But hopefully most of these problems, it'll be exponents that don't create huge numbers when you simplify them, because it really doesn't seem that much simpler if you get this ginormous answer. Okay, so same thing when I have a division problem in here, that exponent goes to everything that's on the inside. And so I have t to the 3, because remember, I just have a little 1. 1 times 3 is 3. And then 6 has an exponent of 1. 1 times 3 is 3. Or you can think about it, if I'm multiplying that by itself 3 times, I have t times t times t, which we write as t to the 3rd. I have 6 times 6 times 6, which we write as 6 to the 3rd. And then I should just simplify that a little bit. So t to the 3 over 6 times 6 is 36. 36 times 6, I think it's 216. You guys check me on that though, okay? Use your calculators. It's been a little while since I memorized these back in like 1995 or 96. Like it was a long time ago before y'all were even thought of. Okay, So then anything to the 0 power equals 1. Super duper easy. Okay, next problems. We need to look at the tables and decide if they are exponential growth, exponential decay, or it could be neither, right? If we're adding or subtracting the same thing each time, even if it's getting bigger and getting smaller, like growing or decaying, those wouldn't be an exponential model, those would be linear. Or sometimes if there's no pattern at all. So we're going to look at these and we're going to say, oh, this one was divide by 5, divide by 5, divide by 5. You can also just use a calculator and do division on each of these, looking at each pair. And if you get the same common ratio each time, that's how you know it is exponential, because the numbers are going smaller by, like we're dividing by, which is the same thing as multiplying by 1/5 or 0.2. We would say that this is decay, exponential decay. Okay, looking at this one, we see that we're multiplying by 4 each time, and our values are getting bigger by a common ratio. And so we would say that this is exponential growth. Okay, remember that if it were adding or subtracting, that would be linear. Okay, number 9, now we need to state the initial amount, A. That's easy, A equals 4. Because if I had T was 0 years, like right at the beginning, that part would just be 1. And so 4 times 1 is just 4. That's our initial amount when time is 0. And then we're going to say, is this one going up or down? So remember, we're always comparing to 100%. So if I had to rewrite that as a percent, that would be 80%. Well, I need to ask myself, am I keeping 100% of what I have every time, or is it going down from that? Well, 80 is smaller than 100, so I'm not even keeping the full 100%. I'm going down by like 20%. So you would subtract 100%, take away 80%, and so we know that it is decay, and it's going down by 20%. Okay, so the rate of change, the percent of change would be 20%, or you could say R equals negative 0.2 or something like that. Make sure you check with your teacher and see how they want you to record your answers. Okay, but it is going down by 20%. Okay, it's not growing. So the rate, I would even be tempted to put in a negative there. But again, talk to your teacher about that. Okay, looking at question number 10, I think this is probably the best way to put that. Looking at question 10, we're going to graph this. So I'm going to start every single time with the easiest one. I'm going to plug in a 0 right there. So if I have 3 to the 0, anything to the 0 just equals 1. 3 to the 1 equals 3. 3 to the 2 equals 9. And then you can see, well, I was just multiplying by 3 each time. So if I want to go backwards, I would divide by 3 each time, which when we plug that in, oh yeah, that means divide by 3, or 1/3. And then 3 to the negative 2, this means I'm dividing by 2 3s, which is 1/3 times 1/3, or 1/9. Or you could think of it as 3 squared in the bottom of the fraction. 3 squared is 9. And then we're going to graph that. So you can tell right away that this base is bigger than 1. So we're going to be growing, and we're going to be growing pretty quickly. Like I'm not even going to be able to go up to 9 if I go by 1s on here. So I'm going to go by 2s. 2, 4, 6, 8, 9, or sorry, 10. Sorry. Did I confuse you there for a minute? 2, 4, 6, 8, 10. I was already looking at this 9 right here. And then in the X direction, I'm just going to keep my regular scale 1, 2, 3, 4 and negative 1, 2, 3, 4. And so we're going to go ahead and graph these. We're going to start at -2 and go up to 1/9, which is really close to the axis there. -1, 1/3, still just the width of my dot probably. 0, 1, which would be halfway through there. 1, 3, and then 2, 9. And so remember, I don't know if you guys remember from other videos, but in these situations, we have something that's called an asymptote, which is kind of a fun word there. It means that we're getting closer and closer and closer and closer and closer to a line without actually ever touching it. And our asymptote here is on the x-axis as y approaches 0. Okay, because if you're taking 1/3 and 1/3 and 1/3, what I have left is going to be really, really small. But if I still am just taking 1/3 of it each time, I still have something left. So that's why it never, ever, ever actually touches 0, but it gets really, really close. Okay, and then looking at number 11, This one's a little bit more difficult. You see that decimal in there. But again, we look at the base and we know that it's going to be growing because it's bigger than 1. It's bigger than 100%. So this is going to be growing. So we're going to go ahead and plug in. Like I said, I like to put in the 0 right there. Well, that part would be 1. So I'd just be left with the 2.5. If I have 2.5 times 2 to the 1, 2 to the 1 is 2. 2 times 2.5 is 5. Then I would have 2.5 times 2 squared. Remember, we have to do the exponent first. Remember PEMDAS or GEMDAS, or please excuse my dear Aunt Sally. So we've got 4 times 2.5, which is 10. And you guys can totally use your calculators on these to get those answers. I want to make sure that you guys understand the concept of it. But sometimes the calculations can get in the way there, especially when we have some numbers that aren't quite super nice. Okay, and so for this to the -1, we have 2.5 times 2 to the -1, which means divide by a 2. So if I have 250 and if I have to cut that in half, I've got $1.25. And then if I'm going to do the same thing for -2, I've got 2.5 times 2 to the -2. Well, now I'm dividing by 4, which goes in there 0.675, I think. Again, check my math, you guys. Get out your calculators. Okay, so I'm going to go ahead and plot these. And I'm going to use the same scale I used before because I look at my biggest value in the y and realize I have to go all the way up to 10. And I don't want to be like putting points all the way in the next problems up there. So I'm going to go 2, 4, 6, 8, 10. And then I'm going to keep the x scale as just 1, 2, 3, 4, 5. So I'm going to go by ones. Just make sure you label it so that we can see what the scale is. So for this first one here, I'm going to go to -2 in the x direction, 0.675. I'm going to go to -1 in the x direction, and then 1.25. Then I'm going to go to 0, 2.5 is about right there. Then I'm going to go to 1, 5 is right in between 4 and 6, and then 2, 10 would be all the way up there. So again, here's our asymptote on the side, and then it's growing, growing, growing. And that is your answer for that one. Last one. Thank you guys for being so patient. I know this stuff can kind of seem a little bit confusing, but keep trying the problems, hit pause, and then check the answers. That's going to be the best way to learn on these. You could try to go back and do the review again on a separate piece of paper, just pausing the video each time just until you guys get it, okay? Last one, number 12, it says the number of cell phone subscribers started at 285, so automatically you should be thinking, that's my initial value. In Grants Pass in 1985, they're just trying to give you some extra information here that we don't really need in our formula, but we should use when we define our variable. And then it's increasing by 75% per year. So now we need to write a function for that. So we have y equals our initial value, 285. And then remember that what we're multiplying by is going to be 100% plus a rate if it's growing, or 100% take away a rate if it's decreasing. So this one is increasing. So I'm going to take 100%. I'm going to add 75% to that. So I'm going to get 175%. But we can't put percents in our equation here. We have to write it as a decimal. So that's going to go in as 1.75. And then I'm going to put it to the t for time, where I could even just use an x for that value, or I could put a y for year. Oh no, I can't put a y because I already used y over here. T for time is pretty common. So, but I want to say that t is the number of years since 1985. So that 1985 right there, I'm just going to circle that in a different color because that doesn't go in our equation anywhere. But we need to state that when we write our equation. You could also put this in if you wanted to as the exponent, like t minus 1985 or something like that. But we're just going to define it as the number of years since 1985. And that is it. Really good luck on the test, you guys. Remember, it's open notes. I think for all the classes, check with your teacher. For my students, open notes. And just make sure that if you have any questions, you ask. Okay, have a great day.